Hello everyone, and welcome. I'm Dr. Sayantika Chowdhury. Have you ever really stopped to think about how your phone remembers your last dialed number? Or how your computer just knows where you saved a file? It can feel a bit like magic, right? But it's not. It's memory. And today, we're going to pull back that curtain and see exactly how simple circuits learn to remember things, forming the very foundation of the entire digital world we live in.
So here's our game plan. We'll kick things off by figuring out what actually gives a circuit a memory. Then we'll meet its most basic form, the latch. After that, we'll add a clock to make things more precise with flip-flops. Get to know the super versatile JK family, and finally, see how all these little building blocks come together to create the systems we use every day.
All right, let's dive into our first section. And to really get our heads around this, let's start with a simple question you've probably thought about, even if you didn't know it was about digital logic. Seriously, think about it for a second. A basic calculator is all about the now. You press 2 plus 2, it shows you 4. It has zero memory of what you did before. But your TV remote, when you press that channel up button, it absolutely has to know what channel you were on a moment ago. One device remembers its past, the other just lives in the present. And the secret to this difference? It all comes down to two fundamental types of digital circuits. And this slide just nails that core idea. On one hand, you have combinational circuits. They're like a reflex. The output is a direct, immediate reaction to whatever the inputs are right now. But sequential circuits, on the other hand, are way more interesting. They have a secret weapon, a feedback loop. This feedback is what gives them a memory, and it means their output depends not just on the present, but also on the past. So what's that key ingredient that gives a sequential circuit its memory? Now, what's really interesting here is the trade-off. Because sequential circuits need that memory unit, they're naturally a little slower and a bit more complex to design. But that extra bit of work buys us something incredible, the power to store information. Which leads us to the big question. How do we actually build that memory unit from scratch? Let's find out how it's built. We're going to start with the absolute most basic building block of memory. You could call it the atom of the digital universe, the latch. Okay, picture this. You take two NOR gates. The output of the first one becomes an input for the second. And here's the clever part. The output of the second one feeds right back into the first. It's like two friends who keep telling each other the same story, reinforcing it over and over. This cross-coupled structure creates a stable loop. Once a value gets in there, the gates just hold on to it. It's latched. And this simple, elegant circuit is what we call an SR latch. It can store one single bit of information. So, what allows an SR latch to hold on to a value like that?
So here's how it behaves. If both inputs, set and reset, are 0, the latch just holds its current value. That's its memory state. If you make reset 1, it resets the output to 0. If you make set 1, it sets the output to 1. Simple, right? But look at that last row. What happens if we try to set and reset at the same time? We get chaos. Both outputs are forced to 0, which breaks the rule that they have to be opposites. This is a prohibited, totally invalid state that we have to avoid at all costs. So if we need to avoid this mess, what's the next logical step in our design?
So how do we fix this? The big problem with a simple latch is that it's always listening to its inputs, which is what leads to that chaos. To bring some order, we need to tell the circuit exactly when to pay attention. And that brings us to maybe the most important concept in all of digital electronics, the clock. And this is the key difference right here. The analogies make it so clear. A latch is level triggered. Think of it like a door. When the enable signal is high, that door is wide open and the inputs can change the output anytime. But a flip-flop is edge triggered. It only listens at the precise instant the clock signal changes. Like a camera flash. It's just one moment in time. This precision is what allows us to synchronize millions, even billions of components in a modern processor. So what's the main difference between how a latch and a flip-flop listen to signals? You see, this whole idea of triggering only on the edge of a clock pulse is what makes our digital world possible. It's like a conductor giving that sharp downbeat in an orchestra, making sure every single musician changes their note at the exact same instant. And a pro tip, when you're looking at circuit diagrams, you can always spot an edge-triggered device by that little triangle at its clock input. So, how does being edge-triggered help us solve the SR latches problems? Well, this brings us to our next big innovation. Engineers needed a flip-flop that was not only controlled by a clock, but also didn't have that pesky invalid state. And that leads us to the hero of our story today, the most versatile, most useful flip-flop of all, the JK flip-flop. The best way to think of a JK flip-flop is as a much smarter, more robust version of the SR. The J input is like set, and the K input is like reset. But the absolute genius of its design is the internal feedback. It takes its own outputs and feeds them back to the input gates. This clever trick handles that problematic 1-1 input condition, not by banning it, but by giving it a brand new, super useful job.
And here is its genius on full display. Look at this truth table. The first three states are exactly what you'd expect. No change, reset, and set. But now, look at that last row. When both J and K are 1, instead of an invalid state, it does something magical. It toggles. The output just flips to whatever its opposite was. If Q is 0, it becomes 1. If it was 1, it becomes 0. This toggle feature is unbelievably useful, especially for building things like digital counters. So what's that magic trick the JK flip-flop does when both its inputs are 1?
Of course, progress isn't always that easy. This amazing toggle feature created a new, very subtle bug in older designs called the race around condition. The problem was, if the clock pulse stayed high for too long, the output could toggle, and then that new output would race back through the feedback loop and cause it to toggle again and again, all within one clock pulse. The final state was a total gamble. It was like a light switch just flickering uncontrollably.
The solution to this was just pure elegance. It's called the master-slave configuration. You use two flip-flops working together. Think of it like an airlock. When the clock goes high, the first door, the master, opens and figures out what the new state should be. Then, when the clock goes low, that first door closes and the second door, the slave, opens, passing that new state to the final output. This makes sure the output only changes once, and only once per clock cycle. Problem solved. So how does this master-slave setup stop that race-around condition?
Okay, so now that we have these reliable, predictable building blocks, like our master-slave JK flip-flop, we can finally zoom out. We can stop looking at individual components and start building some really powerful digital systems.
You know, a really critical skill in digital design is to think of flip-flops like they're digital Lego blocks. They are totally interchangeable. If your design needs a T flip-flop for a counter, but all you have are D flip-flops, you don't need to panic. You can actually convert one type into another just by adding a few simple logic gates.
And there's a very systematic step-by-step process for this. First, you look at the excitation tables, which is just a fancy way of saying you define what you have and what you want. Then you figure out the logic needed to make your existing flip-flop act like the one you want. We use a tool called a K-map to simplify that logic. For example, to make an SR flip-flop behave like a JK, the logic you need is S equals JQ and R equals KQ. You build that little adapter circuit, connect it, and voila! You've just converted one Lego block into another.
So here's the crucial point. These simple 1-bit memory cells are the foundation for, well, everything. You group them together to form registers, which hold data right inside your CPU. You connect them in a long chain to make shift registers, which are essential for things like USB. You hook them up with logic to build counters that can track events, and you use them to create state machines, which are basically the brains of any control unit.
Chalo, let's recap. We started with a circuit that couldn't remember a thing, and step by step, we built our way up to the sophisticated, clock-driven memory cells that power our entire world. Now, mastering these fundamentals is not just about passing an exam. This is the absolute bedrock of chip design, of embedded systems, of computer architecture. Understanding this journey from a simple latch to a master-slave flip-flop gives you the power and the foundational knowledge to innovate in the technologies of tomorrow. Thank you so much for joining me for